Hey kids, welcome to physics. Thought you might want to take some notes with me. We're doing them from slides this time. And this week, you have some notes to take and then a couple short videos to watch and then questions to answer. And that's it. And a Zoom conference if you want to go say hi or ask any questions. So let's take a look here at these slides. We've tried to set them up so that you could just look at the slides and write down the highlighted parts. So let's go for it. This one is all about star color and temperature. So that's true, Leah, but what's cool about stars is that as it comes to temperature, it's backwards from faucets. So like hot is blue in stars and red is cool in stars. Oh gosh, I wish I was there in class to show you all this cool stuff.
Yeah,
all right.
but red is hot. It's hot here, and blue is cold here.
No, that's just for water. Anyways, so the next slide shows you a picture, and we wanted to look at and start to notice that stars aren't all the same color. That's not some fancy Photoshop. That has to do with wavelengths. And if you think back to before we left, it can start to make sense when you think about colors and wavelengths and stuff like that. And this is going to be the key part to the whole course. All right, next up. Astronomers collect the light in a telescope. That's important. People miss that part. And as it passes through different filters, you can use that to determine the star's color. Now what they do is they end up taking all these different weird values like Z and B, and then they subtract them, and yeah, go science, right? Let's write this down. Oops. This first step might seem obvious, but don't skip it. It's important. Just writing down what is highlighted on the slide. The wavelength of that light used to determine the color. All right. The next slide shows us a really important Blackbody radiation curve. You might have seen this in chemistry already. In physics, we look more at the temperature of the star, whereas in chemistry, you might have looked at the composition of an atmosphere or what's nearby to the star. But astronomers notice patterns that stars are red, white, and blue, and they notice that longer wavelengths appear red and are cooler, and shorter wavelengths appear blue and are actually hotter. And you can study more with Wayne's displacement if you like studying this kind of stuff. But let's write this down. Let's just write Blackbody radiation. And I'd love to draw this. So if you have a chance and want some time, maybe draw it here, or you can print out and paste a Blackbody radiation curve if you like. I think I'm just going to sketch it. And I've got a little sketch here, wavelength and intensity, and it looks like wavelength is higher here, and our temperature on this curve is 6,000, 5,000, etc. And so we're just looking at where it peaks, you know. And so this one, they're saying, the one all the way to the left with the highest peak, is a hotter star, and it's bluer. It would have a shorter wavelength. Sorry, it would have a shorter wavelength, so it would be bluer than the third one I noted. It would have a longer wavelength and actually be cooler. Okay, let's write that down. Long wavelengths, red, cool. Shorter wavelengths, blue, hot. Okay. Next slide. Our very own sun. Even though, see, it kind of peaks here in the green, it's not green. As it turns out, no stars are going to be green. And this is because if it's in the middle, it's got enough of the edges, and all together, they make white. Let's write that down. Stars are not green if black body radiation curve peaks at green. On our curve, that might be somewhere, I don't know, somewhere in the middle here. Then we see white. Because, as we learned on color mixing, red plus green plus blue equals white. And boom, that's why our star, the sun, appears white. All right, this next slide takes us to spectral lines that you might have seen in chemistry as well. And where they dip, it corresponds with like a master list key code of each of the elements. And this is really important because we can find out how old stars are based on the elements that they make. As it turns out, there's so much to the story, but essentially the more massive elements they're making, the older the star. But there's a lot to the story, and it's all amazing, at least to me. All right, so let's write something down about spectral lines. And I'm also going to try to sketch this as well. It looks like we've got a density, I'm calling a power density, and wavelength on the bottom. And it looks like line, dip, something like this.
Wait, stay there. I'm coming up.
And you can see they dip at different points. And you know, maybe a dip here might be categorized as sodium, and these dips could be hydrogen. It's just all based on this key that scientists get, maybe this is calcium, from just looking at these basics by themselves purely and getting their light information and comparing it to the star. If you get a star with a spectral analysis like a DNA fingerprint or DNA or fingerprint, then you can identify it and find out exactly what it's made. Spectral lines are used to determine what a star is made of. And therefore, that's the little triangles, thus or therefore, also used, well, maybe it's not a therefore. I'm going to take it out. Nah, I'll just do what I was supposed to do. Older stars have more complex elements. Yeah, neat. All right, so this next section is about how they classify stars. And it starts with puppies. Can you identify the breeds of the puppies? I know there's a few of you out there that are like, yes, I know that's a German Shepherd. How? How do you know? Yes, it's got that snout. It's got those markings and those ears. What is that, a little Jack Russell? How do you know? Yep, look at that tail. And this guy, that's a little Labrador. Look at those ears and the coloring. So we always classify things, and stars are no different. So let's write down classifying stars. Okay. There's a short video for us to watch here. I wonder how long it is. Let's see. Sorry. I don't think it's very long. I think it just goes through the relative sizes. Oh yeah, this is that big to small thing. There's so many good ones out there. That's Mercury. Here's Mars. Venus. That's like Earth twin, as you can see. It's dramatic music. Saturn. Now these aren't stars, but that is a star. That's our star. That's our star, the sun. Hi. Look at these. Oh, he's a little guy. He is a little guy. There's Ceres A. There's an orange giant. We'll learn more what that means later, but Arcturus. Another red giant. Wow, see? Scale. It's so hard to really think about for too long. Please go outside tonight and look at the stars. They'll be brighter, some because they're closer, but some because they're just plain bigger or literally brighter. I was going to give us another one. Oh. I feel like we've seen this before. Anyway, you get the idea. We actually don't end up using size to classify stars. Originally, they used spectra to classify stars. And so, because the hydrogen lines were so identifiable, if you love chem, you can study that a little more and remember how exciting electrons and moving things and energy levels. You can get these cool color bands. Today, we use what's called the notorious system of stellar spectral types, O, B, A, F, G, K, M, L, T, and this is by temperature, from hottest to coolest. The funny way to remember that is, oh, be a fine gal, kiss me, or oh, be a fine guy, kiss me. I don't know. That's just what they have so far. If you think of something better, let me know. I'm always looking for a better acronym for that. But let's write something down. Notorious classification system is by temperature. Hottest to coolest. O, B, A, fine gal, kiss me, and then L and T, something like that. Now you get the idea. Next slide, we're looking at hydrogen. That was key in typing these main sequence stars like our sun. And it made sense, you know. What happens is, like an oven, in the interior, very core of the star, you get fusion, one of our nuclear processes. And it starts with hydrogen and then fuses more and more and more all the way up. When they run out of hydrogen, they're almost at the end of the longest phase of their life cycle, the main sequence. That's where our sun is right now. Oh, sorry, it's not running out of hydrogen. We have a little while for that. Our star is like middle age right now. I like to show you guys that thing in class where I was like, here's the life of our sun. And I'm like, we're right here, like almost to the top, right? Where are the dinosaurs? Right there, right? So keep scale in mind. Let's write this down. Stars are fusion ovens. And they start with hydrogen. When they run out of hydrogen, they are nearing the end of the longest phase of their life cycle. And that is the phase called main sequence. All elements have a unique atomic spectra, speaking of those spectral lines, and that is all because all atoms are tiny energy conversion devices. That's important. We always got to wrap everything back to energy. It's a good cross-cutting concept for us. All elements have a unique atomic spectra because all atoms are tiny energy conversion devices. So back to the spectra of the 6 different stars. It's the same one we sketched before. Many stars have bands of low intensity at the same wavelengths, and that corresponds to key transitions identifying the elements in those stars. Older stars can form more complex elements. So which of these is the oldest? Well, I think calcium is the most complex. That will be whichever star is represented by the red line, will be the answer to that question. I think we already wrote this down. I'll skip that one. So surface temperature is now more popular for classifying stars. As you heard, that's the OBAF GKM notorious classification system, because temperature focuses more on energy production, which is more closely related to the evolutionary stage of the star. Finding out where the star is in its evolution will help us determine and predict other properties about it and its nearby everything. So like this is going to be introduced later as a really important graphic, but this is sort of like everything you need to know. Somebody said once this is like the periodic table for astronomers. It's got temperature at the top, luminosity, spectral class, magnitude, and then as a star is, they say born, but as a star is made and goes through its life and dies, it spends a lot of time in this main sequence here and then just moves around this graph. All right, so let's write down the highlights. Maybe the question is, why classify by temp? Temperature focuses more on the means of energy production, which is more closely related to the stage of evolution of the star. Okay, this is a really handy chart. And here it is in all its glory. It's called the Hertzsprung-Russell diagram, or HR diagram for short. We're going to sketch this and we're going to copy these notes, but I'm probably going to put the phone down for a second while I do that. So pause the video with me and I'll meet you back here in just a moment. Actually, as I'm making this, I realize I want to point something out to you, that temperature increases to the left. That's unusual, so pay extra attention. We've got luminosity, lumen, and that increases up, so we're good there. All right, so I've got my sketch here. I've got white dwarfs in the bottom left corner, a diagonal stream of main sequence, some supergiants and giants. And this is neat because once we collect the, let's see, where are we? Remember? We have to do this, collect the light in a telescope, find out the wavelength. Then we found out the temperature, right? We can look at temperature. We can even see what it's made of to find out how old it is. And then we can use this HR diagram to say where it is in its life cycle or its evolutionary stage, as they say. So let's write this down. What do we want to write with this? Let's write stars move. I'm going to adjust the highlight later. I'm glad I'm doing this because I don't think you need to write everything I originally highlighted. But it'll be ready to go by the time you get to it. Stars move to different regions on the HR diagram as they evolve. Okay, this is powerful. This is like an astronomer's periodic table. Okay, everything you need to know about stars is right there. astronomers know the star's internal structure and stage simply by determining its position on this graph. If you can, you should print this out or something like it. There are many, many versions, all kinds of black and white or colored versions. If you have the means, please feel free to print it out and paste it in your notebook. Otherwise, that's the last slide for today. I hope you guys are having a good week, and I'll see you soon. And I really miss, calling on kids. So if you have any questions, you can email me or Mr. Chan. He's available on, where is it? He's available on the Zoom conferences, and I stop by too if I don't have another meeting, just to come by and say hi, or I don't know, tell us what you think and how things are going and check in. All right, you guys have a good night. See ya.